This video is going to be a quick one where I'm just going to go over some basic identities and definitions for probability. Many of you probably know about these already, but we're going to be using them in the upcoming topics, so it will be useful to just review them. So to get started, I'm just going to show some probability identities on the screen. First off, I'm going to try to follow this convention as much as possible in this lecture as well as throughout the class, but sometimes we're going to be a little inconsistent about notation. But whenever possible, I'm going to use capital letters to represent random variables, and the values for that random variable will be written in lowercase. So for example, if you have a random variable a, I'll write something like a equals capital A equals little a, or sometimes we'll just write a for shorthand. So for example, when I write this probability identity, I'm using the shorthand form where the probability of lowercase a given b is the long form version of that is, capital A equals A, capital B equals B. Okay, so this is the first probability identity you should either have memorized or just have a natural intuition for. So it says that the conditional probability of A given B is equal to the joint probability of A and B divided by the probability of B by itself. And this is another identity. It's actually basically the same thing. You just multiply both sides of the equation above by probability of B, and you get this other identity. It's sort of like the inverse. And then this last probabilistic identity is Bayes' rule, or Bayes' theorem, which is a fairly famous identity. But as much as it's useful to have these memorized, I'm going to quickly go through how you can just think of them and derive them yourself just from the definitions of conditional probability and joint probability. So of course, conditional probability is the probability of some event A given some other evidence. So given that we have observed B, now what's the probability of A? The joint probability is when we consider two random variables simultaneously, and we want to consider what the probability of both A and B occurring is over all possibilities, right? Whereas conditional probability only considers the possibilities where B has already occurred. So let's think about just these two identities first, and we can just think about probability as counting. That's really what it is. More rigorously, probability is actually counting sort of an infinite number of items. But for the sake of being able to illustrate things, let's just draw out some finite items. So consider that we're going to get a random object. Situations where we get a random, we have a probability distribution where we get a random object, and that random object is either a circle or a square, and it's either red or it's blue. So it could be one of any of these four objects on the screen. And let's say that we draw a bunch of examples from the probability distribution, and we get that there's 3 blue circles, 2 blue squares, 2 red circles, and 1 red square. So we might be interested in a particular probability in this distribution, which could be something like the joint probability of a circle and a red object. So in order to compute this, we basically just have to count how many times that happens in our sample. Now, again, like I said before, the true probability is what happens if we have infinite samples, and we want to then count essentially, what fraction of the infinite examples gives us this combination of circle and red. But in this case, we'll just say we'll just look at the finite sample where these are the red circles, and there's 2 of them. So in order to compute the joint probability of circle and red, we have to then count how many samples have those properties, and then how many samples there are total. And there are 8 samples total on the screen. So the probability of circle and red is 2 over 8, which is 0.25. So now moving on, we can actually try to write down all the sums we might be interested in. So we can count that there's 2 red circles, there's 1 red square, there's 2 blue squares and 3 red circles. and there's 8 total samples, and there's 3 red objects. So if you ignore the shape, there's 3 red objects, and there's 5 blue objects. Again, if you ignore the shape, and we can also count the total circles, or ignoring the color, which is 5, which I'm not going to put on the screen, or the total number of squares, which is 3. So using these counts, we can now think about that first identity I had put on the probability identity slide. So this is, one instance of that particular identity where I'm saying now, what is the, we want to know what is the conditional probability of the object being a circle given that it's red. So the identity says that that is equivalent to the joint probability of the circle and red, of the object being both a circle and it being red, divided by the probability of it being red. Okay, so we can we can count all these quantities up. So if we want to consider what we want is that joint probability. That joint probability is the total number of times that you have both a circle and a red object divided by the total number of times you have a red object, which actually is the identity if you say it out loud in English. But the number there is there's 2 circles that are in the red side on the right side of the screen, and then there's 3 total objects. So 2/3 of the objects are circles. 2/3 of the red objects are circles. And now the joint probability on the right, we have that this was the one we computed previously, so that's 2/8. And then this last red probability is there's 3 red objects out of 8 total objects, so it's 3/8. So if we divide 2/8 by 3/8, we get 2/3. So we can see that this identity is consistent with our counting example. And the second identity, again, is basically, again, it's the same thing. All we did was multiply both sides of the equation by the probability of being red, but we can again plug in the numbers just to make sure that it's correct. So again, 2/3 was our target conditional probability before, but now we want to relate that to the joint probability of circle and red, which was 2/8, which again we counted before. And then the probability of it being red is 3 out of 8 again. So if we multiply 2/3 by 3/8, we get 6/24, which is 2/8. So looking back at the probability identities, it's at least consistent with when we draw these cartoons to visualize probabilities. But you can also just convince yourself that it's true, that all these are true, at least the first 2 are true, just based on the definition of joint probability and conditional probability. Okay, so now the third identity, which is supposedly so important that it has a name that is named after Thomas Bayes, the famous statistician, is actually, again, something you can just derive right out of the definitions, especially if you use the previous 2 identities. So let's look at that by itself. So what we're interested in is, with Bayes' rule, is we're going to reason about the conditional probability of B given A, and we're going to be able to reason about it by thinking about the conditional probability of A given B, and some other probabilities. So how do we get there? How do we think about B given A by looking at A given B? So we start by writing out the first identity, which tells us that B given A is equal to the joint probability of A and B, right, together, the 2 events together, divided by the probability of A. Okay, and this is just, again, sort of part of the definition of all these probabilities, and that, right, we should believe that based on the exercise we did before. And then furthermore, we can break down that joint probability. We can use that. We can now look at the joint probability in the numerator of the right-hand side, and expand that out to the conditional probability times the probability of B. So now all we've done is expand the expression twice using the 2 identities that we talked about. And from there, this is exactly Bayes' rule. So we've now derived this very famous, very old classical identity, which means you don't have to necessarily memorize it if you just know the other 2, or know the definitions of conditional probability. So those are just some of the basic identities and concepts surrounding probability. And probability is going to be something we're going to need a lot as we start to think about situations where there's complexities in the world that we just don't want to model. We instead just we just give up and say, oh, let's just think of it as randomness. And that's what we're going to do now when we start looking at non-deterministic situations.